Hello, my name is Alex Nemish. I'm one of the Marlowe developers, and today I'm gonna show you a bit of Marlowe semantics and part of PAB contracts, Marlowe PAB contracts that we are going to use. I'll start with a brief description of Marlowe semantics that's implemented in this semantics.hs file, and then I'll show you the PAB contracts. I assume you're familiar with Haskell, you're familiar with Marlowe semantics in a high level, and I expect you to see the Lars presentations. So I expect you to know how PAB works in a nutshell, and how state machine library works and state machine library based contracts. Let's get started. Here are the main data types for Marlowe. It's a contract. Essentially, those are 6 constructors that you construct Marlowe contract with. And here's the state that is going to be stored on a blockchain. So we have a state of balances of accounts by party. Here we store the choices parties made. Here we store bound variables that are essentially led bindings. And here is mean slot is essentially a first slot that the contract sees, and this just to prevent to go back in time. The input data type contains essentially actions for Marlowe contract. It's either deposit or choice or a notification of a slot change. And here is the transaction input data type. That's what we give as an input. So we have a slot interval. So every transaction must have a defined slot interval and the list of inputs. So you can combine multiple inputs within a single transactions. You can make multiple deposits or choices and notifications. And we get a transaction output which contains the payments that we expect to happen, the output state and the output contract, resulting state and resulting contract. Here's the Marlowe data. That's essentially what's going to be stored on a blockchain. So it's a current state of a contract and the actual contract. So the main function, the main entrance to the semantics is a compute transaction function that gets transaction inputs, current state, current contract, and gives the transaction output. So first of all, we fix the interval. We check the slot interval for errors. For example, we disallow slot interval to contain any timeouts inside. So for example, if you have a contract with a when construct with a slot 10, for example, you cannot produce a transaction that has a slot interval from 5 to 15, because it's going to contain a timeout inside of it. It's going to be invalid slot interval. So here we check this. Then we apply all inputs. If it's successful, we return the transaction output with warnings we found, the payments we expect, new state, and a continuation. So what happens in apply all inputs? Essentially, it's a loop that first of all reduces current contract until it's quiescent. And then when we get this quiescent state, we take first input and try to apply it until we get apply it and essentially continue with this loop if it's applied successfully until we get an empty input list. Then we return current state and continuation. Reduce contract until quiescent is essentially a function that again goes through a loop and tries to apply reduce contract step function, which essentially evaluates a contract. So if we get a close, then we are in a quiescent state. If we get a payment, we evaluate value, update balances, and return that the contract was reduced. We do the same with if, let, and assert, but for when, we only evaluate it if it's timed out. Otherwise, we say it's not reduced. So when we get this not reduced, then we say that the contract is quiescent. So in a nutshell, Marlowe contract evaluation consists of two steps. We reduce current contract until it's quiescent, so essentially it's either closed or we get to a when that's not timed out yet. And the second part, we try to apply inputs and evaluate the contract further. Okay. Let's see how it works from the client side. As you may have noticed, the Marlowe semantics code is quite abstract and it does not depend on the Cardano nuances, transactions and stuff. So let's take a look at the actual Marlowe validator that's been executed on chain. So here's the script instance that essentially just calls this make Marlowe validator code that uses a state machine library make state machine call and provides a two functions, state transition function and finality check for a state machine. So finality check is very simple. We just check that current contract is closed, then the state machine is done, and the state machine transition function is the actual meat of the validator. So it receives the Marlowe params data type. We're going to talk a bit later. Current state of a state machine, Marlowe data. Marlowe input, this is essentially a transaction input expressed in Cardano types, and it's going to return either nothing in case of an error or a set of transaction constraints that must apply to validate a transaction, and a new state, a new Marlowe data, a continuation contract, and an updated state. So here we check that the balances are valid. So we require balances in a state to be positive. Here we produce an input constraints given these inputs. So in case of deposits, we expect money go into a contract. In case of choices, we expect signatures or witnesses of respective parties. We calculate the total balance that the contract claims it contains, and we check that it actually contains these values. We construct a transaction input given the slot interval and list of inputs, and we call the compute transaction functions that we saw in semantics.hs. And we, given a computed result, we construct a new Marlowe data with new contract continuation and updated state, and produce an output constraints that contain payouts to respective parties. And we calculate new balance, new total balance, given the income and outcome of a transaction and inputs, and we combine all those constraints with range validation. While validating inputs, we check that there are signatures from parties presented by public key hashes, and there is a spending of role tokens for parties that represented by a role. Payments to parties go either by checking that there is a transaction output that goes to a public key for parties that presented by public key hashes, or the payment goes to role payout validator hash. That is a custom validator that you can provide on your own within Marlowe params, or we have a default one. This is a role payout validator that is used by default. That it simply checks that a transaction contains a spending of a role token given a currency. For off-chain execution, we provide 3 Marlowe PEB contracts: Marlowe follower contract, Marlowe control contract, and Marlowe companion contract. Let's go through all of those. Let's start with Marlowe follower contract. It's a very simple one. It contains only one endpoint called follow, and it basically subscribes to a validator address, a Marlowe contract address essentially, and it subscribes to all changes to this address, so we get all the transactions that spend the spend transaction output with this Marlowe contract. So we can store all the inputs that are applied to a Marlowe contract. So here you can see that we call this update history from transaction that in a nutshell finds an input, Marlowe inputs in a transaction, and if it finds it, it constructs a transaction input data type and update the PEB contract state with this transition. So if you're connected to a WebSocket of this contract, you will be notified about state transition changes. And this state of this contract, called contract history, it's essentially stores an initial Marlowe params, initial Marlowe data, and the list of all transaction inputs that were applied to this contract. And you can always restore the latest state by applying a list of transaction inputs to an initial state. This contract is used by Marlowe run to show a Marlowe contract execution history, and you can use it for the same purposes on your own. This Marlowe Plutus contract is essentially a control contract. It allows you to create a Marlowe contract, an instance of Marlowe contract, apply inputs to the instance, auto-execute the contract if it's possible, redeem tokens from payments to roles, to your role, by spending transaction output protected by role payout validator script, or just close this contract. Let's go through Marlowe contract creation. So when you're calling the create endpoint, you provide an actual Marlowe contract to be created and a map of roles to public keys of role token owners. So what happens here is we need to set up a Marlowe params. Let's take a look at this data type. So Marlowe params is a way to parameterize a Marlowe contract in the following way. You can specify your own role payout validator by providing its hash. So you can write anything you want. We have a default one that checks that the role token is spent within transaction, but you can do whatever you like, and you can do this by specifying this hash in Marlowe params. Also, when your contract uses roles, we need to know a currency symbol of role currency. So you specify it here. So when we create a new contract that uses roles as parties, we need to create a new currency and distribute role tokens to their owners. That's why we need this map of role tokens to their owners. So let's take a look at the setup Marlowe params function. So what happens here, we get roles that are used within this contract, and if we have roles and we have owners all provided for these roles, we create tokens with role names. By default we create a 1 token per role. Then we use this forge contract function. That's essentially we reusing other PPP contracts. This one is from currency contract that creates a new currency, and all these tokens go to the creator. So whoever creates a Marlowe contract initially gets all the roles for this contract, but we get role symbol from that, and we immediately within the same transaction that creates Marlowe contract, we distribute role tokens to their owners. So we give them to respective parties. And we create Marlowe params that contains the role symbol, currency symbol of currency we just created for role tokens. Currently we use the default role payout validator hash. So this is a set of constraints that create new currency and distribute role tokens and create transaction output with the Marlowe data. So we use state machine library to create state machine client, and we construct a transaction that distribute tokens and create a transaction output with the Marlowe data and pay value. This is a deposit value. Currently it's 0, but at later point it's going to be some value. I believe it's going to be 1 ADA. all transaction outputs must contain some ADA in it, just to essentially it's preventing the DDoS attacks. And we submit this transaction. That's the way we create a Marlowe contract on chain. Apply endpoint is very simple. Apply inputs endpoint. Just call this apply inputs, which is very straightforward. We construct a slot range, and we use a state machine library run step to run a state machine transition function. And we provide Marlowe input, which is a pair of slot range and list of Marlowe inputs, list of inputs. Redeem endpoint allows you to get money from that's been paid to a role payout script. So we get this address given a role's currency, and spend all these outputs to a token owner. Auto is quite interesting, though complicated thing. There is a set of contracts that can be executed automatically. Imagine any contract that contains only deposits and payouts. So if this contract is eligible, so no participant needs to provide choices or any like interactive stuff. So only scheduled payments. These contracts can be executed automatically, and this endpoint allows exactly that. So if the contract can be executed automatically for party, we call auto-execute contract. This is essentially a state machine that pays deposit or wait for other parties to do their part. The last interesting contract is Marlowe Companion contract. This is a contract that monitors a participant wallet and notifies when a role token goes to your own address. So it runs, it listens to transactions that go to your own address, and if there is a token and this token is generated by Marlowe contract creation, it tries to find the Marlowe contract, and if it succeeds, it notifies this contract, it updates its state. And again, if you're subscribed to this contract WebSocket, you get a notification about a role token, and you'll get Marlowe params and Marlowe data. So if you check this Marlowe Companion state, this is essentially a map of Marlowe params to Marlowe data. So you can always get notified about receiving a role token. Hope this helps. Thank you very much for listening.